Hello, this is Dr. Golding, and what we're going to do here is do some of the proofs from the end of section 7.6, Roman numeral 1. These are proofs that involve using conditional proof, or CP, and indirect proof, or IP. So I'm going to do just 4 of them, since I emailed you some of the previous proofs in that section, thanks to Antonio. So anyway, here I've got started number 11. So number 11 is A wedge B horseshoe C, then we have not A wedge D horseshoe E, and we're trying to prove C wedge E. So I'm going to use indirect proof because I don't see anything obvious to do with my premises. Okay, these are premises. I'm trying to get to C wedge E, but I don't see anything obvious to do here that's going to lead me to C wedge E. I see C is over here and E is over here. Sorry, over here. But how do I get C wedge E out of this? So what I'm going to do is an indirect proof. And remember, the way indirect proof works is I'm going to assume the opposite of what I'm trying to prove and show that that leads to a contradiction. So here we go. I'll say not the entire conclusion, not C wedge E. This is going to be an assumption for indirect proof. I'm going to hopefully be able to get to a contradiction of some sort. Might not be enough room in here for these steps, but let's see what happens. This is going to be step 3. I'm assuming the negation of C wedge E, and then what I would get by indirect proof is not C wedge E, and then I would get the C wedge E by a double negation. Okay? So here we go. Now I have not C wedge E. When you have the negation of a wedge, it's a very powerful formula. So you can do a De Morgan to get not C and not E. That's De Morgan on 3. Then you simplify. Whenever you have a conjunction, it's a good idea to simplify. We'll get not C by simp on 4. We'll get not E by a simp on 4. And now we have 2 modus tollens's, right? We have not C over here. We've got a horseshoe with C as the consequence, so we can do a modus tollens to get not A wedge B. That would be a modus tollens on 5 and 1. And now we have a negation of a wedge. That's a very powerful statement. We can break that down into not A and not B. I'm just going to do the not A here. Not A and not B. That would be a De Morgan on 7. And we are going to need some more room here. What I'm going to have to do here is simplify to get not A. And I still can do another modus tollens on 6 and 2. So I'm going to write it over here because it's just running out of room. But if I do, this would be step 10. Theoretically, this would be inside the scope marker. So imagine the scope marker is over here, and we have modus tollens on 6 and 2 to get not. Modus tollens on 6 and 2 would get not A wedge D. 11, we would do not A and not D. That would be a De Morgan on 10. And then we would simplify to get that not A. And look, we have a contradiction. So this would be step 13. We would have not A and not A, which is a contradiction. So this was simp on step 8. And this is conjunction of 12 and 9. All right, sorry, I kind of ran out of room here. Again, number 10, we got by doing a modus tollens on 6 and 2. Then we have, again, this very powerful statement. This is a negation of a wedge. We break it down into not A, and not B. Simplify to get not A. Then we put not A and not A on the same line. So it turns out that this is step 14 and this is step 15. Okay, I hope that was clear. Let's try another one. Let's try 12. We're going to do number 12 on the board now. And number 12 has two premises, K wedge L, horseshoe M and N, premise, and try to write a little smaller to get this all on the board. We have N wedge Q, horseshoe P, and not K. That's the second premise, and we're trying to get to not K. That looks like it's N wedge O. Sorry about that. This is N wedge O. Horseshoe P and not K. Okay. So what should we do with this? Again, I look at my conclusion and I'm going to say, I don't see any obvious things to do with my premises, so I'm going to start off by assuming K. Now in this case, we're trying to prove a negation, so let me just assume K, and then we'll hopefully get down here to some kind of contradiction. And then we'll say not K, and that would be the very end of the proof. I hope you can see that. That says not K on the bottom. It's the desired conclusion. So this is step 3. And now we say assumption for indirect proof. How do I make some use out of my premises now? I'm going to wedge on L just intentionally to get the antecedent of that first premise so I can do a modus ponens. I'll say K wedge L by addition on 3. That's addition on 3. And then I now have the antecedent of 1, so I can do a modus ponens to get M dot N modus ponens on 4 and 1. Then I can sort of check this off. This is N wedge O. So actually I'm just going to simplify to get that N. Simplification on 5 to get N. And now I can wedge on the O to get the antecedent. And wedge O. And addition on 6. And now I have a modus ponens on 2 and 7 to get P dot not K. Modus ponens on 2 and 7. And I'm still looking for some kind of a contradiction. This is going to be a bit bizarre, but look at what we have here is I now have, I'm going to simplify to get not K, simplification on 8. And look at this, what I have here is I have K, I also have not K. So I'm going to put that on the bottom here, inside the scope marker still. This is step 10. This may sound a little bit bizarre that we have K and not K as our contradiction, but this is conjunction. on 3 and 10. And that's no problem, meaning by that the fact that you have the very thing you assumed here turned out to be the thing that contradicts this thing over here. It's opposite. And therefore I say 11, I found a contradiction, and therefore I'm going to say indirect proof on steps 3 through 10. Okay, now if I said to myself, here's just a little pointer, which is, again, this says 11, not K, indirect proof on 3 through 10. If somebody said, okay, suppose someone did this. They said to themselves, hey, I got to not K, so why don't I just say that I finished my proof? I got to not K over here. The problem is that you can never stop a proof in the middle of the scope marker. The whole point of this is assuming this. The justification for the assumption of K was I'm assuming it temporarily in order to reach a contradiction. Well, if you didn't reach a contradiction, then you haven't utilized the rule properly if you just stop over here and say, hey, I proved not K, so this would be incorrect to stop here and say I got to the conclusion. If you're assuming for indirect proof, you need to reach some kind of contradiction, which in this case was K and not K. Now that may sound a little strange, that the contradiction happened to be K and not K, but it's a contradiction by rule, so conjunction on 3 and 9, and then you go to the last step where you say, okay, then I've shown that this leads to a contradiction, therefore based on these premises, it's not the case that K. So that's IP on 3 through 10. All right, let's try another one. We're going to do number 14. Here comes number 14. It is an interesting one. F. It looks like it should be impossible. F. Therefore, what does this say? G horseshoe H, wedge, not G horseshoe J. G horseshoe H, wedge, not G horseshoe J. Okay, now then, this is step 1. Let me just erase this here. We're still going to do number 17 also. We'll get to that later, but this is number 14. F, therefore, G horseshoe H, wedge, not G horseshoe J. Now, in thinking about this a little bit, it's obvious to me that, F doesn't even occur over here anywhere. There's no reference to F in the conclusion. How could it be that you could get to this conclusion based on F? It seems like it should be impossible. So the only way that this could work is if this is actually a tautology, meaning that this statement is always true no matter what the premises are. In fact, if we were able to go on to 7.7, which we're not going to do for this class because it's just too much at this point to try to do 7.7, but maybe I'll talk a little bit about it even though it's not going to be on the final. So 7.7 is not going to be on your exam. But nevertheless, in 7.7 you learn that you're able to prove theorems without any premises whatsoever. So the fact of the matter is that this thing is somehow going to be a tautology. This thing is going to be provable without any premises. Now, the only way you can start a proof without premises is by making an assumption, either for conditional proof or for indirect proof. So, in this case, what we are going to do, in other words, what we're going to do here is we're going to have a proof where the premise doesn't even play a role in the proof, except for the fact that it's listed as number 1. But it's kind of like a fifth wheel. The way to prove this thing over here would be to start off with either an indirect proof and show that it leads to a contradiction. In other words, assume the negation of this and show that that leads to a contradiction. Or what you could do is try to change this somehow to a horseshoe, to a conditional statement, and then use conditional proof. And I'm thinking that that might be the easiest thing to do. So let's try it that way. Hopefully we're going to get to, on the bottom, we're going to get to what we need, which is G, horseshoe H, wedge, nut G, horseshoe J. That's going to be our conclusion. Now, how can I convert this to a conditional? I want to get it into a conditional form because that way I will be able to use conditional proof. So remember, the rule of implication is the one that allows you to change a disjunction to a horseshoe or a horseshoe to a disjunction. But what we need to do first is we need to double negate the left-hand side of this. So I'm going to do working backward, okay? Working backward by double negation, I'm saying double negation just on the left-hand side, G horseshoe H, wedge, not G horseshoe J. Now this is going to come from a double negation on whatever this step is. See what I've done here is it's the same formula, but I double negated the left-hand side of the disjunction. Okay, now remember the rule of implication, or I called it sometimes conditional exchange, is that if you have P horseshoe Q, you can get to not P wedge Q. So this over here could be changed to not G horseshoe H, horseshoe, not G horseshoe J. See that? I took off a tilde and changed the wedge to a horseshoe. It's like this. Take off the tilde and change the wedge to a horseshoe. So this would be implication from here, negating the antecedent and replacing the horseshoe with a wedge. Now I have a horseshoe. So now I can do a conditional proof. I'm going to start off assuming not G horseshoe H, assumption for conditional proof, and I'm going to try to show that that leads to not G horseshoe J. All right, you see that I have my antecedent here, my consequence inside the scope marker, and that's what I have over here. So I have an assumption for conditional proof. Now, the statement not G horseshoe H could be broken down. We do that by doing an implication on the inside of that. We get not G wedge H. Again, that's the rule of implication. Okay, I need to take this tilde and put it here. I'm exchanging the horseshoe for a wedge and tacking on a tilde to the antecedent. So step 4, now I'm going to do a De Morgan to get not G and not H. This is De Morgan on 3. And now step 5, how can I get not G horseshoe J? Well, I'm seeing here that what I could do is a little conditional proof inside this scope marker. I could do a number of things here, really. I'm going to do not G and try to get to J. This would be an assumption for conditional proof. Now notice again, I'm not using F at all. F, it doesn't play any role whatsoever in these inferences. So how am I going to get from not G to J? Well, I see here that I have not G here and I have not G here. So that's a contradiction, which means I could be able to prove anything I wanted. So I'm going to do a little bit of an IP inside here. I'm going to assume not J for indirect proof. And then I'm just going to, now I'm running out of room, sorry about this. I'm assuming this would be step 6. Step 6 is not J, assumption for indirect proof. I'm going to do 7 over here. I hope you can see this. 7 is simply going to be simplifying number 4 to get not J, not G. This is a simplification on 4. Okay, running out of room here, so I'm not going to write that. But if you want to take that down, this is a simplification on 4 to get not G. And now for 8, I can join not G and not G. That would be a conjunction on 5. I have not G, 5, and 7, so I have a contradiction right in here. So this basically goes inside here, and that means I can infer not J and change that by a double negation to J. Okay, sorry, I'm kind of running out of room. I should have written these smaller. It's very hard to do these without a lined board. Okay, so again, in summary, what we have here is F played no role in this proof. We, let me put in the numbers here at least. So 8 is going to be in here, and 7 is going to be inside that scope marker. Not J would be an indirect proof on 6 through 8. Then we have a double negation. This would be step 9. 9 is not J. Double negation on 9 gives you J. Now you have step 10. This would be a CP on 5 through 9. And this would be step 11, step 12, step 13. This is a CP on 2 through 10. And here we have an implication on 11. And finally, a double negation on 12. Okay, that was a little complicated. We ended up doing an ACP and then an AIP inside the ACP. Now, there might have been a simpler way of doing this, but this is somehow the way it came to me to do it. We changed this to a horseshoe, and then we had to double negate the left-hand side first in order to change it to a horseshoe, and then we could do a conditional proof. Inside this conditional proof, we ended up having to do another conditional proof and another indirect proof inside that conditional proof. Okay, a little complicated. Let's try number 17. Number 17 looks like this. Okay, we're going to have R dot S biconditional. Okay, number 17, R dot S biconditional G dot H. We're going to have R horseshoe S H horseshoe G. And we're going to have R biconditional H. As the desired conclusion. Okay, now, the first thing we should do here is we could take number 1 and switch it out a bit, because this is a biconditional. Anytime you see a biconditional in your premises, you're probably going to want to change it to a pair of conditionals. So let's do that right away. We'll do R dot S horseshoe G dot H. This is going one way, and we're going to have G dot H horseshoe R dot S, and this is called biconditional equivalence or biconditional exchange, right? The biconditional means that you have this horseshoe that and that horseshoe this. So we simply have a conjunction of two conditionals going from the left-hand side to the right-hand side and going from the right-hand side to the left-hand side. Now we break that down, separate it out into its two parts. This is going to be simplification on 4 for both of those steps. Okay, I wrote that big because both of these are simplification on 4. Okay, and now what we're trying to prove is R biconditional H. So how are we going to do that? We can't really break these down anymore right now, but what we could do is we're going to do 2 conditional proofs here. Because R biconditional H, if we work backward, you have, this is the same thing as R horseshoe H and H horseshoe R, which means that if I can get R horseshoe H and I can get H horseshoe R separately, then I would conjoin them, then I would be able to infer R biconditional H. So let me try to get R horseshoe H, and there's not going to be enough room to do this proof. I'm going to have to do this in stages. This is R horseshoe H. This is going to be R horseshoe H. Somehow I'm thinking I can get R horseshoe H out of this. If R is the case, and S is the case, I can get H. If R is the, if S is not the case, I'm trying to think if there would be a possibility of getting some kind of a contradiction. If I assume H, or let's see here. Okay, I think I see what I need to do. I need to make use of premises 2 and 3. Okay, can I get H out of R somehow? Let's try this. This is an assumption for conditional proof. And now I was blanking out there because I wasn't looking at like 2 and 3 here. Okay, now I have a modus ponens. So I can do that, a modus ponens. Once I assume R, I can do a modus ponens to get S by 2 and 7. And now I can conjoin R and S. R dot S conjunction on 7 and 8. And now I get G dot H, sorry, I'm going too fast. G dot H by modus ponens on 9 and 5, right? We got R dot S horseshoe G dot H, modus ponens on 5 and 9. And now I do a simplification to get H. So I proved that if I assume R, I can derive H somehow. And now this would be 12, this would be CP on 7 through 11. But I'm only halfway there because I now have R horseshoe H. I still need to get H horseshoe R and then combine them. So I'm going to erase this, even though really technically speaking, I should be continuing. Maybe I'll try to continue over here. This would be step 13. Okay, so imagine that 13 is just continuing below here. So step 13, I'm going to initiate a new conditional proof I'm going to assume H and try to get R. Assume H, try to get R, and then you get H horseshoe R. Okay, so if I assume H, well, now I have the modus ponens with 3. So let me write this down. Assumption for conditional proof. This is going to CP on 13 through something. I can do a modus ponens because I have number 3 and number 13 gives me G. Modus ponens on 3 and 13. And now I have G and H. I can combine them to get the antecedent of 6. So we'll go H, or we'll do G dot H, combine them that way. G dot H conjunction on 13 and 14. And now we're going to have R dot S. And now we're going to have, this would be modus ponens. Modus ponens on 6 and 15. And then a simplification on 16 to get R. And now we have 18, H horseshoe R, CP 13 through 17. And now what we would do, again, these really ideally should be listed below, number 12. So it would be all the way down to the floor. Anyway, you now have H horseshoe R on step 18. You have R horseshoe H on step 12. You would then, so this would be step 19, combine the two, conjunction on 12 and 18, and then you have biconditional exchange on step 19, so this would be 20, biconditional exchange on 19. Replacing the conjunction of 2 horseshoes with the biconditional, and that's how you would get to R biconditional H. So that, in the end, did not involve, at least the way I did it, it did not involve using indirect proof. It only involved using 2 conditional proofs separately and then combining the results to get the conclusion. Now, we're not going to do 7.7 on the final. However, I just want to talk about it a little bit, just to show you how it works. The system in section 7.7 discusses theorems. So a theorem is something that you can prove without any premises. So how would that work? Okay, a theorem. A theorem, by definition, is any formula that can be proven using the rules, of course, but which does not require any premises to be proven. Basically, a theorem is going to turn out to be a tautology, something which we saw with the truth table method. A tautology is a statement which is always true no matter what the values of the components are. Okay, so now that we have the proof method, here's how you would prove theorems. Basically, I'm going to give you a very simple example of a theorem. A very simple example of a theorem would be, again, any tautology would work, but let's take this one, P wedge not P. If you do a truth table for this, you're going to find that this is always true. Either P is true or not P is true, right? But how would you prove this using the proof method? Well, it's going to be pretty easy. The trick is going to be always that you would start from an assumption. Now, there's different ways of doing this. You could assume the opposite of this and show that it leads to a contradiction. All right, maybe I'll show you that. We're going to assume, for indirect proof, we're going to assume the opposite. I'm going to assume not the whole thing. Not P wedge not P. Hope you can see that. Probably you can. Okay, that says not, parenthesis P wedge not P. That's step one, and this would be an assumption for indirect proof. So as an assumption, I need a scope marker. I'm going to start the proof with a scope marker, and then it's going to have to require one little extra step down here, because by rule, an indirect proof allows you to tack on a tilde. So you're going to get not P wedge P. This would be indirect proof on 1 through whatever this is. And then this would be, I'll exchange this to, look at that. It goes right to a contradiction. By implication, remember the rule of implication? You can, this is not implication, what I'm talking about. This is De Morgan, sorry about that. De Morgan allows you to, it's not the case that either P or not P. So I'm saying, well, it's not the case that P, and it's not the case that not P. So right here we have a contradiction. So already I can say by step 3 that, well, my assumption led to a contradiction, IP on 1 and 2, and so therefore not P, wedge not P is true. And now to get the original formula that I wanted, do a double negation on 3. And you get P wedge not P. Okay, so that's how a theorem looks. You would start with an assumption for indirect proof, or you would start, let's do a different one. Again, I'm not going to ask you to do theorems on the final because we have not been able to spend a lot of time on it, but I think it's just something important, interesting to know that the proof system does allow you to prove things without premises once you have assumption for conditional proof and you have assumption for indirect proof. So let's just try one more theorem. A very simple theorem would be something like, this is really simple, P horseshoe P, right? This is saying if P is true, then it's true. Well, that's going to be true for any statement, whatever you plug in for P. If you plug in the same thing here, which you should, because that's the form of the statement, if P then P has got to be true, it's a tautology. You do a truth table method for this. It's going to be true under the major operator on both rows. Right, let's do a little simple truth table. The only value you have here is P, right? And we have P is going to be either true or false. So if it's true, then the horseshoe is true. And if it's false, we said that the definition for the horseshoe is that if the antecedent is false, then the horseshoe is true. So it doesn't matter whether that's false or not. So it turns out to be that it is always true under the major operator. Okay, how would we prove this using the proof method? Very simple. This is a conditional. One way to prove a conditional is to use CP. In fact, that's the most natural way. If I assume P, can I get to P? I hope so. If I assume P, this would be assumption for conditional proof. Now, how can I get P out of P? So, in this system, what you could do, well, this can't be step 2, but what we're going to say is, I'm just going to double negate it and then take off the tildes. It's kind of like a little bit of a logician's trick. We need something to get P down here, even though we have P over here, so we could do double negation on 1, double negation on 2. Now we have P, so therefore we could do if P then P, that's a CP on 1 through 3. Another thing we could have done is do something like, we could do addition and just cleverly wedge on P itself. Addition on 1, and now we could say P wedge P, remember the rule of tautology. Tautology on 2 allows us to exchange P wedge P for P. So we have P, we've proven that if P is true, P is going to be true. So we say CP on 1 through 3. So again, section 7.7 is not going to be on the final. If you found this stuff I've been doing today very weird and bizarre, you might sometime take a look at section 0.7 and read through it and think about it. I just wanted to show you how theorems can be proven using the proof method. On your final, you will not have to have any theorems. You will not have any theorems. 7.7 is not on the final. I just wanted to talk about it a little bit. Had we more time, we would have gone on to 7.7, but we did not have the time to do that. Okay, well, I showed you some proofs from 7.6. Some of you have sent me your work, and I still need to get back to you on some of you on some of the exercises you've sent me. And I will try to do that later today. And again, I'm available by email, by phone, if you want to contact me and talk about any of the material, either today or over the course of the next week. The final is on Thursday at 11:30, a week from today. I hope you're well and good luck on the end of the semester. Good luck on all your finals. And most importantly, stay well.